Hello everyone and welcome back. It's Davide here, and in this new video tutorial you will learn how to perform a discrete Fourier transform in Modulo. This is the sixth part of this short course about Modulo. In the fourth part I gave you a general overview of the software package, and in the previous video I explained how to perform a POD. Today we will perform the DFT on the same cases analyzed in the previous video. So the 1D pulsating parcel flow and the 2D time-resolved PIV. So let's start. First of all, as usual, we have to select a folder for the exporting through the menu Export. Let's select Testing Modulo on the desktop, and then, as we did for the POD, create another folder for the test case that we are going to analyze. Let's start from the 1D test case. So, test DFT 1D. Now we can import our dataset. For this decomposition, we will also see the influence of removing the mean flow. For the POD in the previous video, we didn't remove it, but as we will see in this video, for the DFT it is a key point. Let's start without removing the mean flow. Now I will speed up this part of the video while I import the data, since it is the same of the previous video. Okay, D has been constructed and we are ready to perform the DFT. As you remember from the second video on the theoretical background, the DFT does not require the computation of the time correlation matrix, and the temporal structures are constructed a priori from the temporal discretization. Since every mode has one harmonic, Modulo does not export the temporal basis, even if we activated it in the menu Export, but only the sigmas and the spatial structures. The frequency associated to each of these modes is collected in the sigma file, as we will see shortly. Let's take a look at this. Let's perform the DFT. The first thing that we should notice is that, as I said in the previous video, unlike the POD, we need to compute all the modes and not only the ones that we want to export, since we cannot know before which modes will be more important. So we can input the sampling frequency and range of modes to be exported only after these are computed. For this case, the sampling frequency is 2. And we want to export the first 8 modes. As we can see from the screen, for the DFT, Modulo exports 2 different plots of sigmas and 2 different plots of the spatial structures. Let's wait for the exporting. Okay, now we can give a look at the results files. In the exporting folder, we have, as usual, the Excel file containing the mesh, the Excel file containing the sigmas, and the Excel files containing the spatial structures. The mesh file was described in the previous video, so let's start from the sigmas. We have 2 figures. I open both of them. Well, on the right we have the classical permutation plot of the sigmas in decreasing order. Here we can appreciate the amplitude decay of the decomposition. On the left we have the same sigmas plot versus the frequency of the associated temporal structure. Both plots are collected in the Excel file that does not present one unique sheet, but presents 2 sheets. The first sheet represents the spectrum in the frequency domain. Indeed, the first column collects the frequencies, while the second column collects the amplitudes of the modes. The second sheet contains the same amplitudes but in decreasing order. So the first column collects the frequencies and the second contains the amplitude of the associated mode. As I said in the previous video, remember that these sigmas are normalized. If we look at the spectrum, we can notice that there is a peak at the zero frequency, since we did not remove the mean flow. This is the only mode that does not have a complex conjugate. Indeed, if we look at the spatial structure of the first mode, we can notice that the imaginary part of this mode is null, since basically this represents the mean flow. The other amplitudes are conjugate pairs. In fact, the real and the imaginary part present a phase delay. For example, if we look at the spatial structure of the second mode, we can see that the real on the left and the imaginary part on the right of this spatial structure present a phase delay. This is obviously summarized in the Excel file that presents a different form with respect to the ones exported with the POD. In fact, the Excel files of the spatial structures present two sheets, the first containing the real part of the spatial structure and the second containing the imaginary part of the spatial structure. These are always velocity profiles since this is a 1D test case, so they are collected in a column vector. Well, we now repeat the same exercise but removing the mean flow to see how this operation influences the decomposition. We select an exporting folder, testing modulo, and we can save in another folder called test DFT 1D no mean. Remember to remove the mean flow, and then we can import our dataset. Now I will speed up this part of the video. Okay, let's give a look at the results. If we look at the sigmas, we can see that since we have removed the mean, we no longer have a clearly dominant mode at the zero frequency. On the other hand, if we look at all the other modes, we can see that these remained identical. In fact, I can open also the previous plot, and we can see that the difference is only at the zero frequency. We can confirm this looking at the spatial structure of the first mode. If we look at the imaginary component of this spatial structure, we can see that this is no longer null, because this is not anymore the mean flow, because we have removed the time average. So we can state that in the case of the DFT, removing the time average is only done for plotting purposes, as the first mode at the zero frequency tends to be much larger than the others in most statistically stationary datasets. However, it is essential to notice that the indexing has changed since the modes are exported in decreasing order of amplitude. So what before was the second mode now became the first mode. But besides this shift in the indexing, all the other modes are the same, and I'll let you check this by replotting them from the Excel files. On the other hand, I let you now repeat the same exercise for the POD and compare with what we retrieved in the previous video. You will see that the POD modes change, even if in this case not significantly. In general, it is a good idea to remove the mean for datasets that are stationary and statistically fully developed, while this operation does not make much sense in case of transient dataset. Well, to conclude this video, we now perform the DFT on the 2D vector test case of the time-resolved PAV. But before proceeding, I show you the spectrum of the sigmas in the case in which we do not remove the mean flow. As we can see from the plot, we have a huge peak at the zero frequency, representing the mean flow, but it is impossible to distinguish in the plot the other amplitudes, so it is strongly recommended to remove the mean flow for this test case. So we can select an exporting folder for this test case in the folder testing modulo, and we can create another folder called test DFT 2D. So let's remember to remove the mean flow, and let's import our dataset. Now I will speed up this part of the video. Okay, D is ready and we can perform the DFT. Let's wait for the computation of the modes. The sampling frequency for this test case is 2 kHz, so let's put here 2000, and let's export the first 10 modes. Giving a look at the results, we can see that the interpretation of the plot containing the sigmas in the frequency domain is now easier. The spectrum does not present a peak at zero frequency, since we have removed the time average. This allows for a better visualization of the plot. In fact, we can distinguish the amplitudes of the modes that we have exported in red from the amplitudes of the modes that we have not exported in white. The other important difference is that the Excel file containing the spatial structures does not present only 2 sheets, but 4 sheets. The first and the second sheet collect respectively the horizontal and the vertical component of the real part of the spatial structure, while the third and the fourth sheet collect the horizontal and the vertical component of the imaginary part of the spatial structure. They, as usual, are exported as matrices. To conclude this video, observe that this time exporting the modes in order of amplitude for the DFT is not particularly interesting, since these, highlighted in red, are all close to the mean. In this dataset, this happens because of a large scale modulation and because of the important impact of the slow dynamics of the wall jets. In addition to these, it may be interesting to analyze these modes near a frequency of 500. That, as you know from the previous video about the DFT, are linked to the large vortices in the jet flow. Keep in mind that these are the modes number 157 and 158, so to study them you will have to export, for example, from the mode 150 to the mode 160, and then find them back from their associated frequencies in the Excel file. I let you do this as an exercise. You will see, however, that the DFT modes have more difficulties in representing these vortices, because these are not well described by a single frequency. To see these more clearly, we will need a range of frequencies, and we will need to use the multiscale proper orthogonal decomposition. But this is the subject of the next video. For the moment, I thank you for your attention, and I hope to see you in the next tutorial. Goodbye.